in deformed space-time symmetries.
Thanks. So in this talk I will discuss about the problem of localization of particle states in the relativistic quantum spacetime. So I will take advantage of the nice presentation of Fedele of yesterday and as Julia's today, that already motivated this kind of approach where basically you can model a scenario where which is motivated by quantum gravity, where there is a minimum length in space-time under which you cannot perform any measurement through non-commutativity of space-time coordinates. So, as Fedele has pointed out yesterday, in general, if you have a relation of this kind, this is a possible characterization, then this is not invariant under standard Poincaré Lorentz transformation. So the question is it possible to have a relativistic version of this? And well, if this quantity that characterizes the scale, which is believed to be at the Planck scale, is an invariant observable for all inertial observers, then one needs to deform the transformations that connect reference frames. And so, well, the focus of this talk, I will try to introduce a new ingredient in the discussion, which is maybe was mentioned briefly yesterday by Fedele, but I think it's quite striking, which is this, that we found out in this work of 2010 with Melino Camelia, Marco Matassa, and Flavio Mercati that if you deform the symmetries with a scale which has the dimension of an energy, then inevitably you have to renounce to the concept of absolute spacetime locality in favor of relativity of spacetime locality. Similarly to how basically you have to renounce to absolute simultaneity when you introduce an invariant scale with dimension of speed in the transition from Galilean to special relativity. Well, this is quite quite hard to digest, because basically what happens is that, as we found out in this earlier work, is that the locality of a process becomes relative to the distance of the event from the observer. And this is a Planck-scale contribution to the uncertainty in the locality. So in the coordination of a distant observer, a process could seem to be non-local, but when I act with a deformed translation, then I find that the observer or the reference frame, which is local to the actual measurement, restores the locality of the process. Okay, so this is the idea, what we found out about this relative locality. So let us see how the interplay of this feature, which is relativistic, with the characterization of quantum particle states in this kind of setting. So I take this model of non-commutativity as a prototype, which is Kappa-Minkowski, which is the one that Fedele also considered yesterday. And the deformation of symmetries of this spacetime is the one of Kappa-Poincaré, which is an off-algebra, is a nonlinear generalization of the algebra of symmetries. How can we characterize spacetime points in this space? So we did this in this quite old work, actually now, of 2013 with again with Melino Camelia, Valerio Astuti, where essentially we found a representation of this coordinate, which is different with the one that Fedele was discussing yesterday. This was in 2013, where we represent these non-commutative coordinates in terms of auxiliary kinematical Hilbert space, which is this is a 1+1 dimensional description of this scenario. These are two copies of the Heisenberg algebra, basically. And in this sense, we can represent in this kinematical Hilbert space. Now I will point out why I call it kinematical. Both the coordinates, but also the action of the deformed relativistic transformations that connect the coordinates, the non-commutative coordinates of different observers, and as well as the parameters of the transformation. Well, for those who are interested, a crucial ingredient in this game is the differential calculus, because as you see, for instance, the translation generator do not obey a standard Leibniz rule, so they are not differential operator, and they act not as simple commutators, but there is which reproduces the non-standard Leibniz rule, while the differential calculus can be restored in a very, very profound way, and this was developed in 4 dimension in this later work of mine. And so you can construct states in a momentum space representation that describe basically points where particles are localized by introducing a measure of integration and a scalar product which is invariant under the action of all these deformed symmetries, translation and boost. So, and what you find is that there is not a state in the chimerical Hilbert space that you can define it absolutely sharp in its localization in space-time. This is because essentially, if you try to do it, then well, by the nature of this representation, you find that the uncertainty in one of the 2 coordinates goes to infinity, either in time or in space. Okay, so all points in this non-commutative space-time must be fuzzy by a Planck-scale contribution. So what we did is we defined the maximal, what we thought, well, a way of modeling a maximally localized state through a Gaussian state in momentum space, and then you can compute expectation value of their positions and the uncertainty in their time and position variables, okay, in this way. And what you find, if you do it, is that, well, if I define a state which is localized at the origin of a reference frame, well, in this talk I'm identifying an observer with the origin of a reference frame. So, so if I localize a state of a particle in the origin, okay, then there is the contribution to the uncertainty in the localization grows with the distance from me, from the observer, okay? So if I have a state which is localized here, a state which is distant from me is much spread out. But we have a representation also of the deformed translation. So if I translate to this point, I find that the same state now becomes localized, and the state that was distant from me has a larger uncertainty due to the Planck-scale contribution. Okay, so this is the relative locality version of the fuzzy point. Well, what's more important, because I talked about the kinematical Hilbert space, but in this second work, actually, we were interested in describing the physical particles. So physical particles are not just points; they have to be on shell. Okay. And what we did, well, we based our result on a proposal on how to formulate covariant quantum mechanics, which was put forward by Reisenberger in 2000, and Rovelli as well, which basically is able to describe covariant quantum mechanics up to a certain limit of energies. Otherwise, you get quantum field theory. By imposing a non-shell constraint, which is the Hamiltonian, the covariant Hamiltonian of the system, which in our case is a deformed Hamiltonian in terms of the Planck-scale deformation. So basically, we describe physical observable by introducing a new scalar product, which enforces this Hamiltonian constraint. Okay, and what happens is that the coordinates are not self-adjoint operators in this physical Hilbert space because they do not commute with the Hamiltonian. So we found that a good observable that can describe the localization of points is what we identified as the intercept operator, which is a deformed version of the Newton-Wigner operator. Okay, and in terms of that, we can well, actually, what you obtain is a time-parameterized trajectory or operator that describes the word line of a particle on the physical Hilbert space in this way. And the speed is energy dependent due to the Planck-scale deformation. Okay, so the picture that you get is that you don't get, so the fuzzy point, when you put it on shell through this mechanism, where you enforce the Hamiltonian constraint, it becomes a fuzzy worldline, okay? So you put it on shell and you describe it in terms of this intercept operator. You describe it in your space-time. You obtain a worldline which is fuzzy. Here, well, this is just a qualitative picture. So here I put the quantum contribution, the h bar contribution of the fuzziness basically to 0. And here I'm showing only the Planck-scale contribution to the fuzziness. I finished. So here I depict the fuzzy worldlines of two particles with different energy, a low energy particle and a high energy particle from the point of view of a first observer who is sitting here. And if I perform a translation, I find that the hard particle acquires a contribution to its quantum fuzziness, which grows with propagation. So basically, the physical picture is that in this scheme, you obtain an irreducible Planck-scale contribution to the fuzziness of the worldline, which grows with the propagation. And thank you for the attention. This is, and there are, well, just me mention that we are working at future developments with PhD students Tadeusz Sadek, Professor Koaki-Wittmann, as well as Michał Popiel, who is here, and Domenico Frattulillo. Thank you. Sorry.
Thank you.
Thank you.
Okay, we have time for one or two brief questions, so if you keep it short and the answer short.
Yeah.
Okay, thanks for the talk. At the beginning, you have the only dimensionful scale is the Planck scale, I understand. And later you introduce particles. So you would have a mass scale or you have a black hole, but it doesn't appear the mass scales in these commutation relations. Could it appear?
The mass scale, you mean of the particle? Ah, okay. Let me think. Well, the mass should intervene in when you impose this mass shell relation. Okay. So the mass is the eigenvalue of this operator in this scheme. So when you consider only these points, you got no mass. But when you go on shell, then you obtain another scale, which is the mass of the particle. In this final picture, these are massless particles that I depicted. But if you get the mass, then you have, of course, another contribution to the mass, which appears as the eigenvalue of this Hamiltonian operator. So this Hamiltonian operator is the mass squared.
Yeah, just a short question. I think it was a third slide after the Heisenberg microscope. You had this kind of scheme. Can you? Yeah, that one.
This one.
Can you briefly explain what
yeah,
this
is. So basically, what happens is that since the transformations between observer, translation, boost, well, eventually rotation, not in this scheme, depend on the energy, on the momenta, through the Planck scale. So just in the when you turn on the deformation scale, then what happens is that each particles transform when you move to another reference frame, either with translation or boost or the combination of the two, which we're studying now with my PhD student, so that the point where they are localized and the worldlines shifts proportional to their energy. Okay? So basically the interpretation that we give to this effect that emerges from the formalism is that locality is objective only locally to the measurement. So for the observer that witnesses the measurement. This is somehow complementary to what you do in quantum reference frame, because this is not with, I mean, it's not complementary, it's different, but there is not h bar here. It's just a Planck scale contribution. Okay, so if you get one thing that we want to study is how you combine it with the effect that you study in quantum reference frame, where you get also an uncertainty contribution which is due to purely quantum mechanics. Okay.
So we will definitely have more time for discussions in the afternoon. So let us thank Giacomo and all the speakers of the morning session. Before we leave to the break, there is an announcement.